Okay, sorry, wrong push. Should be this. Yeah. Okay, so this is the announcements view. Okay, announcements scene. Welcome back to the last episode of Introduction to Computer Networks. Okay, at NTU. All right. Good morning to Vincent and Davis as well. You might see Polly is overly excited today because this is the last lecture. The end of the semester is closed and summer is just ahead. Oh, and Loretta. Okay, welcome. We don't have new announcements. All have been said yesterday, so let's dig into the topics today. So first video is actually the last of chapter 5.2 to provide a closure of the routing algorithms. And then we'll start talking about the internet routings. So this summary video, a little bit long, but you will see a full comparison of link state versus distance vector routing. Okay. Now with both routing algorithms introduced, let's compare the two algorithms. LS here stands for link state. DV is the distance vector. Let's compare the message complexity first. If you recall in link state, each router there needs to generate this link state report, and it gets propagated, broadcasted throughout the network. So each of these link state reports is going to travel all the links. Okay, there are E of them, and there are N nodes. Each will be generating these link state reports. Therefore, overall cost N E. In the worst case, in case the network is very well connected, the E here is about the scale of N squared. Okay, so overall, the cost can go as high as N cube. So link state message complexity, not good at all. Distance vector, on the other hand, the message exchanges between the local neighbors. Right? And as you see in one of the examples earlier, as soon as the route converges to the shortest, no more distance vector messages being passed further. So there seems to be some opportunities for some node to stop message passing early. So in terms of message complexity, DV is slightly better. Now, the second metric, the speed of convergence, the time it takes to converge to the shortest path. In link state, it runs the Dijkstra algorithm, which we know the time complexity being N squared. There's some optimizations one can apply that takes you to N log N time, even better. So link state seems to be okay, except that we need to be careful about setting the link cost. Try not to use the traffic going on the link right now and changing it dynamically. On the other hand, in distance vector, well, the convergence time varies. In some of the earlier examples we see, in a 2-hop network, it takes only 2 cycles to converge. So if you think about it, the convergence time for a network is pretty much in the scale of the diameter of the network. But that is actually in the ideal situation. What if we have bad news that we need to propagate through the network? Then we could run into the count to infinity problem. And during the phase of counting to infinity, the packets will be looping from router to router. So in distance vector, the convergence time is a little bit hard to predict. It really depends on the situation. On the other hand, link state, very predictable. I would say in terms of predictability, link state wins over distance vector. But under normal situation, distance vector's convergence time, is indeed the diameter of the network. There's not many hops. Even for a large network, the diameter might not be so long either. The third matrix to compare, the robustness. What if a router is malfunctioning and reporting the wrong link costs? Things like that. In link state routing, during the phase that router is malfunctioning, the neighboring nodes will be advertising the wrong link state reports. And each router will be calculating the shortest distance based on the wrong link state report. But once the malfunctioning goes away, link state report will be corrected, and quickly each router will be calculating the shortest path based on the correct link state report. So the time you expect the network to recover from the router malfunctioning is expectable in link state. In distance vector, however, if a router is malfunctioning and reporting, for example, a short link cost to a particular neighbor, Yeah, the node can actually falsely reporting the shortest path to a particular destination being shorter than expected. So these incorrect paths gets advertised and propagated out. And the neighbors of these nodes is going to take it and potentially include that in the shortest path and updating the DB and then pass the incorrect information further. Yeah, each node's table is going to be used by the other. Each node's distance vector is going to be used by others. Yeah, this error is going to propagate out throughout the network, and it might take a long time for the network to recover to the correct cost. Taking a long time and not very predictable. So in terms of robustness, link state here is still winning by a head, by a neck. All right, so that's comparing link state to distance vector. And then we start chapter 5.3 and 5.4. Okay, so this is internet routing. Okay, now before we start, recall what is an internet. Holly talked about this many times, right? The internet is a network of smaller networks. Okay, a network of smaller networks. And you heard Polly referring to these smaller networks as domains or sometimes subnets. Today, there's a new term, autonomous system. So these subnets, domains, are also called autonomous systems. Okay, this next video, a little bit long, 6 minutes. Yeah, the first part is actually to give an overview of chapter 5.3 and 5.4, and then formally define this term, autonomous system. Next, we'll be talking about two routing protocols that are actually running on the internet. First is called the OSPF, and it's based on the first principle, the link state routing, the one implements the Dijkstra algorithm. The second, BGP, is then based on the other routing principle, the distance vector routing. Well, to be exact, BGP is not just distance vector routing. It's an extension of distance vector routing. It's the path vector routing protocol. And just to tell a little bit more, OSPF is the routing protocol that runs predominantly within a network, a local network. While BGP, this other one, very, very critical, very, very important, is running on all these backbone routers, all over the internet. Let me take you back to the way we describe these routing algorithms. In that, I introduced the graph abstraction, right? So routers are considered nodes and links considered edges. And therefore, we have a graph where we have edges interconnecting the nodes. So all these nodes, very simple, and considered equal. And the graph there you see, the network is completely flat. There's no clear hierarchy. But on the internet, it's so not the case. So until now, the way we're introducing these routing algorithms is actually very idealized. Taking a link state routing and put it down to the internet and consider every router as a node, that's not going to scale. Even taking a distance vector routing algorithm, which is already more scalable than link state, if we just put it into the network and having all the routers on the internet implementing distance vector, it will still not scale. Why? Take a look at this. How many possible destinations we might have on the internet if the internet is completely flat? If we draw the graph of the internet, there's going to be how many? These many destinations. Therefore, in each of these distance vector routers, in order to store the shortest distance to each of these destinations, in order to store the predecessor, to each of these destinations, how much memory is required? Well, let's say we use 1 byte to represent the shortest distance, 1 byte to represent the predecessor. We'll need 2 bytes for each destination. And there are these many destinations. If my calculation is correct, this is probably something at the scale of about 8 gigabyte. Yeah, or something like close to gigabyte. Wow, this is a lot of memory, right? Just to store routing information. And not to mention that we have forwarding tables and all these other things that might be necessary. Yeah, not going to work very well, right? And if you think about this, hey, this is IPv4 address space. What about IPv6? Ouch, you don't want to go there. So even if we use a more scalable routing algorithm, distance vector, consider it working on the internet, not gonna scale. Okay, we cannot be storing all destinations. And you know what? Each of these distance vector routers also send distance vectors to the neighboring nodes, and neighboring nodes sending to neighboring nodes. Okay, these distance vector exchange, it's also going to swap the link, right? Because each of them is this big. You need to send really, really long messages to make sure that the entire 8 GB of this very basic distance vector table gets to the neighbors. Okay. Ouch, and ouches probably. You see, it's not going to work if we treat all routers the same and run just one routing algorithm throughout the internet. It's just not going to scale. Okay? So what we do really on the internet is this. We'll group the routers that are nearby belonging to one organization together as a system, as a local area network. So these are other routers nearby belonging to another organization, another system. Now each of these systems can work independently. The network admin hired by the organizations could decide independently, autonomously, what routing algorithms they would like. So routers being interconnected in this system can be configured running link state routing. So all the routers running the Dijkstra algorithms. This other system here, the system admin can decide maybe distance vector routing is better, more scalable, better. So all routers here then will be running the distance vector routing. So systems. What happened on the internet is also this. Each system, the network admin is going to configure, one or two routers and make them the delegate routers. These delegate routers, at the higher level, will interconnect. So this system's delegate routers and this system's delegate routers, they might interconnect. And there could be lots of these systems around all over the internet. Their delegate routers will interconnect at the higher level in the backbone of the internet. And all of these routers in the backbone is going to run one routing algorithm. So distance vector or link state. Well, to just tell you ahead of time, for internet, the backbone routers run something that's more like the distance vector because it's more scalable because we don't know how many systems eventually the internet will grow into. So you see, two levels of hierarchy. There's backbone network, and then each delegate router there associated with it is a local area network. So internet, again you see here, in terms of routing, is also a network of networks, a network of these autonomous systems. Okay, so being autonomous is the key word. Okay, so these subnets or domains, they can work independently. So if Polly asks you, you are the network admin, hired by an autonomous system. Which routing algorithm would you prefer running in your domain? Link state or distance vector? Okay, so guys, type it up on the chat. If you are a network admin of an autonomous system, which routing algorithms would you use? All right. And the next video coming ahead, it's 4.5 minutes. Okay, you heard in the previous video that these autonomous systems interconnect. Within an AS, it runs a level of routing algorithm, and above, between these dedicated routers, there's another level of routing algorithms. So you see, there's intra-AS routing, as well as inter-AS routing. Okay, so this video, 4.5 minutes, is to define a little bit more clearly what does intra-AS routing do and what does inter-AS routing do. Once again, on the internet, we aggregate the routers in a region and call it the autonomous system, an AS. Or sometimes we also call it a domain. So the internet is a network of ASs, a network of domains. The routing protocol within the AS, the network admin configuring all the routers running, is called the intra-AS routing. So you see here, it's the routing protocol running among all the hosts and routers in the same AS. All routers in the same AS will need to run the same intra-AS protocol. Now, routers belonging to different ASs can then run different intra-AS protocol. That is an independent, autonomous choice of the network admins individually. Now, each AS will also pick powerful routers, usually sitting at the border of the AS. these powerful routers, I call them the delegate routers earlier. Yeah, here you see a more formal way of calling them are the gateway routers. So gateway is what? The doorway. Yeah, the router sitting at the border of these AS connecting to another AS. Okay, so gateway routers, powerful delegate routers, will be sitting at the edge, the border, okay, of its own AS and have links both within towards routers within the AS and links to routers in other AS. And therefore, this routing protocol, okay, running in the backbone of the internet is called the inter-AS routing. Okay, so that is the routing protocol that's running, okay, across the gateway routers. So this is the routing, okay, working among the ASs, and the gateway router there will be doing the inter-AS routing computation. And on the slide here, you see an example of ASs and how ASs interconnect. So we do have 3 ASs, 1 here, 2 here, and 3 here. You see individual routers interconnected within one AS. Okay, so there are 3 here for AS2 and 3 more here for AS3. Now, AS1, 2, 3 each could run its own intra-AS routing, okay? But you see, 1B and 1C, both of these routers have links internally as well as externally. So 1B and 1C are the gateway routers. So these two gateway routers. Just like 2A for AS2 is one of the gateway routers. 3A for AS3 is one of the gateway routers. Okay. And inter-AS routing is running in between. Okay. 1B, 2A, 1C, 3A, and so on and so forth. Now, the focus of this slide is to talk about how would the forwarding table look like when we have 2 levels of routing running on the internet. Okay. Now, let me show you an example here. Okay. 1D is one of the routers existing on the internet. What's going to happen there is the forwarding table is not going to be just contributed from the intra-AS routing algorithm. It would also be contributed from the inter-AS routing algorithm. As you see earlier, in order to pass data from one router to another router that's far away, okay, not within the region, right? You need intra-AS routing to find the gateway router. And you also need the gateway router, okay, to find, hey, where's the destination gateway router? All right, so you do need inter-AS routing algorithm telling, okay, each node where to pass data further. Just like you need intra-AS routing there telling you, okay, how to reach another router within the AS. Forwarding table here will be configured by both intra and inter-AS routing algorithm. The intra-AS routing determines the entries, okay, for destinations within the AS, okay, within AS. And inter-AS, okay, determines entry for the external destinations. Okay. To be precise, the inter-AS determines which gateway, okay, which router here you should be passing the data to. Okay. But intra-AS will also be telling 1D here, okay, to go to that particular gateway router, what is the right way? So you see here, interplay of inter-AS and intra-AS routing for packets going outside of the AS. All right, so you can see that there's inter-AS routing, intra-AS routing that are running at each level. But you see in the last couple minutes in the video, right? These 2 routing algorithms somehow need to interact, otherwise it won't work. That's called the interplay of intra and inter-AS routing. This next video, 4 minutes, Polly would define an example that you will see the rest of the lecture today. Okay, so pay attention. And Polly will be using that example to illustrate again the interplay of intra and inter-AS routing. To make sure the interplay of the intra-AS and inter-AS routing is more clear, okay, let's take a step back. Okay. Look at AS1 here, 1A, 1B, 1C, and 1D. Okay, so these routers within AS would run the intra-AS routing. Therefore, they would know the shortest path going to each other. No problem. Now, at a higher level, at the inter-AS routing level, so we have these gateway routers. 1C and 1B are the gateway routers of AS1. 3A obviously a gateway router for AS3. But you see here, 3B having also connectivity to outside to another AS. 3B is also a gateway router for AS3. Similarly, 2A, to B, to C, all have links to outside, to other ASs. So they are also gateway routers. So these gateway routers at the higher level will be running the inter-AS routing, so that's another routing protocol, and they will all be running the same routing protocol. They will exchange information to each other using the link state or the distance vector routing to come up with the shortest path. But this time, the shortest path is what? Oh, if I want to go from AS1 to AS2, the shortest path is to go directly from AS1 to AS2. Now, if there is another AS here, AS4, for example, okay, then the shortest path might be to go from AS1, AS2, and then AS4. So these gateway routers will maintain shortest path, but shortest path in terms of, what is the next AS to the destination AS? What is the next AS to the destination network? Okay. So we might have another AS here, AS5. Then the shortest path from AS1 will be what? AS1, AS3, and then AS5. Okay. With those said, we may now walk through the scenario here. Let's suppose a router in AS1, say 1D, and it's got packets to go outside of the AS. Let's say AS5 here. Okay. Now, we see the shortest AS path will be the what? A1, AS3, and then AS5. And this information will be available here at the gateway router, 1C, 1B, 3A, 3B. But 1D here as an internal router, so this router here, we'll have actually trouble judging, right? Among the two gateway routers, 1C and 1B, which one of these 1D should be passing the packets to, so that these gateway routers will be able to pass further to the neighboring router along the shortest path to the destination. This is also saying, even though these routers are internal, they participate in intra-AS routing. They do not participate in inter-AS routing, but they need still to know the shortest AS path to these destination ASs out in the world. Okay. So 1D, 1A don't do inter-AS routing, but they still need to know the inter-AS path. Okay. So they must learn the inter-AS path, which is to know for each destination AS, is it AS2 or AS3 being the next hop AS to the destination AS? And this is essentially the inter-AS routes. And how? Okay, how does 1D and 1A learn? Well, you know what? 1C and 1B do participate in inter-AS routing. So 1C and 1B thereafter, inter-AS routing will then propagate these AS path information to all routers inside AS1. Okay? And so propagation of the AS path, just like computation of the inter-AS path, would also be part of the job of the inter-AS router. Yeah, so you see, inter-AS routing there not only are exchanging AS paths, to find the shortest AS path to the destination networks. These inter-AS routers in a domain, they will also send these AS path information to the internal routers that are only running the intra-AS routing. Okay, so that's exactly how this interplay between intra and inter-AS routing is done. You will definitely hear more when we talk about BGP, that is the inter-AS routing protocol that we are using on the internet. But for now, let's talk about the easier routing on the internet, the intra-AS routing. Okay, and you guys, I ask you guys, in case you are the network admin of an AS, which of the routing algorithms you would use? And I think all of you say LS, right? Link state. Why? Probably very clear, because LS is a lot easier to manage. So you will have less headaches, using LS. So you see, that's why human world is working in a way that's not exactly optimized. Optimal solutions usually are complicated and hard to manage. When you need to deal with people, complex mechanisms give you a lot of time overhead, communication overhead. So let's check out intra-AS routing. So let me introduce the options there have existed. Okay, some of them still exist, but not that popular, and some already, are obsolete. So the options of intra-AS routing. This video, 3.5 minutes only. The first big category is the intra-AS routing. Okay, so this is the routing protocol runs on the routers within NAS. It's also known as the interior gateway protocols, IGP. And here, interior gateway, not to be mistaken with the gateway routers. So gateway routers are the routers sitting at the border of an AS, having connectivity to other ASs. So gateway router there are to interconnect ASs. But interior gateways are completely internal. Okay? And then running on these internal routers within an AS, we have three very well-known protocols. RIP here, not really standing for resting in peace, it's actually Routing Information Protocol. Okay? But if it adds the impression, RIP, this protocol is also the oldest implementation of an intra-AS routing. It came with the Berkeley's BSD distribution in the 1980s, late 80s. And it's based on this principle, distance vector routing. Okay. Yeah, nowadays I'm not quite sure. I don't know if any network admins is running RIP for their intra-AS. Okay. But this other one, OSPF, short for Open Shortest Path First Routing Protocol. This one, on the other hand, is very popular. Okay. So open here stands for open source. Okay. RIP is also open source as it came with the BSD. So it runs also the shortest path first routing. Yeah, you guessed. Yeah, it's the Dijkstra shortest path algorithm that's running, and therefore it's based on the link state routing principle. And to make sure that we credit the right people, OSPF is actually based on ISIS. It's another routing protocol that was designed maybe 3 decades ago, by early researchers for distributed system research as well as these multiprocessor system research. So in those paradigms, having multiprocessors, if you want to pass the messages around, and these processors are actually forming an interconnected network, you also need to find a path to go from one processor to another processor. Okay, so at the time, those researchers, those computer scientists, have designed ISIS for the purpose. Okay, OSPF for internet, which is also a distributed system. It's just that it's very loosely connected distributed system. Yeah, borrow much of the design principles from ISIS. Third one is called the IDRIP, IGRP, Interior Gateway Routing Protocol. Now, this one is completely closed. It's Cisco proprietary. Okay. It came with these Cisco routers, but it only is maintained until 2016, and obsolete afterwards. The reason for that is because Cisco is also beginning to embrace the idea of doing software-defined networking. So if you recall, in software-defined networking, routing is all done in the remote controller on the powerful machines. So the routers there, in SDN, pretty much are doing what? Generalized forwarding, and allowing the flow table being installed, and that's pretty much all, There's no need of running routing algorithms on individual routers. So starting from 2016, Cisco stopped maintaining IDRIP because there's really no need, very little need of doing routings inside the router. And now we talk about OSPF because this is the most popular intra-AS routing. As you guys have also picked LS, OSPF runs the link state routing algorithm. Yeah, let's speak a bit more about the most popular routing protocol here in the intra-AS category, the OSPF. Open here stands for, the protocol is open source. Second, the SPF stands for the routing protocol is based on the link state principle. So we do distribute the link state reports all over the network. Therefore, each router will be able to reconstruct the global network topology. From there, then we call the Dijkstra algorithm to compute the shortest path. Be a bit careful though, these routers sending these link state reports, they'll be sending these reports in OSPF message. These OSPF messages are native IP packets, meaning the message itself, and then we append the IP packet header, and that's all.
There's no TCP, UDP, or application layer header on top of that. Yeah, inside these link state advertisements, it's going to contain, hey, who the neighbors are for this router. Also, the cost of the link leading to connecting to these neighboring routers. Again, ISIS routing, this is the predecessor of OSPF, designed by the early distributed system researchers. Now, what we haven't mentioned much yet are these. So these are the advanced features of OSPF. First of all, okay, these OSPF messages, very important link state reports, okay, they can be sent through a secure channel such that the receiver of these link state reports can authenticate, okay, the sources of the sender, therefore preventing malicious attacks. Okay, so yeah, if people can just send these link state reports around, okay, with no security check, one can easily inject a false route, okay, into the system. Second feature is this. One can actually exploit multiple same cost paths. Okay, so in case we come up with the topology such that the Dijkstra give us same cost paths and there are multiple of them, we could actually send data over these multiple same cost paths, okay, which is nice, okay, sometimes. For each link, the metric for the link cost, okay, can be defined also differently for different type of services. Okay, for example, if we are trying to serve best effort traffic, meaning traffic does not require timely delivery, okay, so the receiver can wait longer, then the cost of a satellite link, which the delay is longer, can be set lower, right? Because you would then prefer using the satellite link if the data does not require timely delivery. On the other hand, okay, if the data is real time, okay, then set the satellite link costs high. Therefore, we avoid choosing satellite link along the path to deliver the real-time data. Okay. And oh yeah, it allows also, OSPF allows also integration of the unicast and multicast. Now, if you recall in Dijkstra algorithm, in the end of the algorithm, what we ended up generating is from the source, from the router doing the computation, a shortest path tree. That is also saying that from that source, we could also send a copy of the packet along that tree to all the receiver in the network. So that is also a what? A very efficient flooding tree. Okay, that is a efficient multicast tree. So what multicast meant here is to send from one source to multiple receivers. Okay, so that the extra shortest path tree is also a multicast tree. So from that shortest path tree, we could do unicast, sending from one source to one destination. One can, of course, exploit that to send from one source to multiple destinations. And in the meantime, guaranteeing that it's also the shortest multicast tree. Okay, so multicast OSPF, MOSPF, is a very nice and easy extension of OSPF. Oh, by the way, one can also configure OSPF to run in hierarchy, okay, such as this one here I'm illustrating. So you see, there are two levels of hierarchy here. At the lower level, area 1, area 2, and area 3. Okay, inside each area, we could be running an OSPF, and all these internal routers within an area runs the same OSPF. It requires the same metric, link cost. And then at the higher level, you see, okay, in the backbone of this local area network, in the backbone of this AS, we could have also multiple routers configured. So these are called the backbone routers in general. Okay, some of these backbone routers might be at the border, okay, of the AS. They are also the boundary routers. Some of these backbone routers, okay, are also, okay, the manager of the areas. Okay, so this guy here and here and here are the area border routers. Okay, so the area border routers, boundary routers, as well as the other backbone routers together form the backbone, and they will together run also OSPF, but that is independent of the OSPF running inside each of these areas. So this slide is pretty much repeating what I was just saying. In the example, we do have two levels of hierarchy. Okay, so at the lower level, we have these local areas, and at the higher level, the backbone. Inside each local area, the link state advertisements will only travel within the area. Okay? The link advertisements for the backbone network will be traveling only within the backbone. And each node, okay, in each area is going to know the entire area's topology. And the node inside an area will only know the direction, okay, to the border area routers in case the destination is outside, okay, of the area. So these area border routers, okay, will summarize the distance to the destinations inside its own area and advertise to the other area border routers. Okay, so that's how the area border routers discover each other at a higher level. Okay, and those advertisements will be shared by also the backbone routers and the boundary router.
Alright, so that video is a little bit long, isn't it? Because OSPF, although it runs link state routing, which is very simple, but you see that these smaller networks, these ASs, are getting bigger and bigger. And security is something that's important. So you see that in OSPF, there are these additional functions being added to the basic link state routing so that a routing algorithm can be more secure and can work a hierarchy intra-AS. Okay. Now, the major routing protocol we'll be spending the rest of the time today, BGP. Okay. At the inter-AS level, can each of the AS decide which inter-AS they want to use? Obviously not, right? Because this inter-AS routing, they need to be able to, work together and compute the shortest AS pass or an AS pass. So inter-AS routing, there can only be one protocol, and on the internet, it's called BGP. So this video here, 5 minutes, a little bit long. It's going to be an introduction of BGP where you will see quite a few terms, okay, that are new. All right, be a little bit patient. 5 minutes.
Now the second big category, the inter-AS routing. There's in fact just one protocol defining the category, the BGP. Now this is also the routing protocol that runs on all these gateway routers, okay, that are higher in the internet routing hierarchy. OSPF, RIP, EDRIP, those are the intra-AS routing. So those runs on the regular routers, okay, within an AS. Now, network admin gets to choose one intra-AS routing protocol versus another, okay, as long as all the routers within the AS runs the same routing protocol. Similarly, at the higher level, these gateway routers, okay, in order to find a way to reach each other, they need to run the same routing protocol as well. You see, there's no need of having an alternative, okay, inter-AS routing protocol. Therefore, BGP here is the only inter-AS routing. Very critical. It plays the role of enabling all these packets being exchanged, okay, in the core of the internet. We'll talk more about BGP, but let me share just a little bit ahead of time. BGP here is based on the distance vector routing. To be exact, okay, it's based on the path vector routing. So in distance vector routing, the router tracks for each destination what is the shortest distance and what is the next hop, okay, along the shortest path to the destination. In path vector, okay, so this one running at the inter-AS level, the source AS will track for each destination AS what is the entire AS level path, inter-AS level path. So that inter-AS level path will contain all the intermediate ASs, okay, along the way from the source AS to the destination AS. So what's nice about keeping track of the entire AS path is this. The source AS knows by default what is the next hop AS. And by counting the number of ASs along the way, you get a rough sense of the path cost as well. But the downside of tracking the entire path is that the memory requirement is higher. But this is okay, right, at the inter-AS level because we try to aggregate destination IP addresses, right, into prefixes. Okay? And if we do that as much as we can, we are not actually storing a big vector containing one entry per IP addresses. Okay? Potentially, we just have a low number of these prefixes, okay, to span the entire IP address space. So path vector is exactly what BGP, this one and only inter-AS routing, is based on. First line, BGP stands for Border Gateway Protocol. And once again, it is the one and only inter-AS routing protocol that's holding the internet backbone together. To be more precise, it allows each AS the following. First, it allows the gateway router there for the AS to receive subnet reachability information from the neighboring ASs. This is very similar to distance vector. A router receives distance vector, okay, from the neighboring routers. So the gateway routers in the AS receive path vector from the neighboring AS's gateway routers. So by subnet reachability information, we meant the path for each destination subnet for each destination AS. Okay? And there are many of these destination ASs, therefore, we receive the path vector, okay, from the gateway routers of the neighboring ASs. Second step, the gateway router receiving such a path vector will then propagate it to all the internal routers, okay, including those routers are gateway routers to other neighboring ASs. Okay. As a result, okay, each of these routers within the AS can calculate what is the best path for a particular destination AS. The calculation can be based on what's provided in the path vector. For example, the path length, right? Or based on the policy of the organization owning the AS. Now, this is more and more likely the case how a router determines what is the best route. Okay? The policy can well be profit-driven, business-driven, security-driven, and things like that. And in the end, when a good AS path is selected for a destination AS, the border router there, then can append, the AS's AS number to the AS path derived, and then further propagate this to the neighboring ASs. So that completes the cycle of receiving path vector, doing the calculation, and then pass the path vector on to the rest of the internet. Right? And of course, at the beginning, the AS gateway router will announce itself, right? So each AS is potentially a destination. It will announce itself's existence to the rest of the internet.
Alright, so essentially in BGP, it's very similar to distance vector, but we receive path vectors from neighbors, redo the computation based on policy, and then once we get the new path vector, we announce or propagate to the neighboring BGP routers. Okay, so the bone of BGP is still distance vector, but we kind of extend it in multiple ways, right? From distance vector to path vector, from shortest path computation, Bellman 4, to policy-based computation. Okay. Now, the next video, only 4 minutes, it's just an illustration of what I just said in the video.
One last point to make is just this: the reachability information, aka the path vector. When they travel across the border, go from one AS to another AS, this is actually part of the exterior BGP protocol. So in exterior BGP protocol, we established the exterior BGP connections to allow path vectors travel across borders from one AS to another. Now, for path vector, that is supposed to be sent internally to all the internal routers, then belongs to the IBGP protocol, and they are sent through the interior BGP connections. And these are actually illustrated using this picture here. Okay, so if we focus on AS2, we do have two gateway routers, 2A and 2C. So you see these gateway routers connecting to other ASs. There are exterior BGP connections to outside, exterior BGP connections to outside. So eBGP, in red color. But in addition to that, 2N and 2C both need to send path vectors internally. Okay, so you see they went through the IBGP connections. All right, so IBGP connections in blue. So once again, these are gateway routers, and the gateway routers you see having both the red connections and the blue connections. They run both the eBGP part of the protocol as well as the IBGP part of the big BGP protocol. Those BGP connections are often referred to as the BGP sessions. So these routers will exchange messages over semi-permanent connections. The reason that they're called session is probably because it's semi-permanent, so it's on all the time, and occasionally you take it down and then restart it. Okay, so semi-permanent TCP connections. Now, TCP, BGP is a routing protocol, right? these messages we send should be at the layer 3, but TCP is actually a layer 4 protocol. Okay, how do you like this? On the other hand, TCP allows reliable data transfer. So would you prefer the pass vector? So these messages that we're exchanging between the BGP routers, the pass vector is being sent reliably or not? Yeah, to push it a bit further, what about using TLS, okay, the secure version of TCP? And if we use TLS, these BGP messages, these pass vectors, would look more like an application level message. So you think about it, you debate within yourself. Now, the messages we're exchanging between the BGP routers over the BGP sessions are these. You have the pass to all sorts of destination networks, the pass to all sorts of destination ASs. In fact, altogether, we just call it the pass vector. Okay. So BGP, again, a pass vector protocol. And let me give you an example here. So let's say in AS3, okay, there is a prefix X, okay, and this is the destination for packets coming from maybe AS1 or AS2. So AS3 that learns about this destination will need to announce, okay, advertise it to outside of AS3. So 3A here, okay, will need to announce, okay, its existence and pending its own AS number, so AS3 here. So this will be the AS pass, okay, being advertised. This will be the AS pass being sent in the BGP message to the other end of the exterior BGP connection, to the other end of the BGP session. So 2C here, okay, will receive the AS pass, AS3, comma, X. So AS3's gateway router 3A will advertise the pass to AS2's gateway router 2C. So when AS3 does this, it's also saying that AS3 promises AS2 to relay packet, okay, on behalf of AS2 so that it can reach destination X.
All right, so that's one example, okay, of BGP working. All right, so the next video, it's 4 minutes long. So we'll run over to the break time, but I'll make sure that you get 10 minutes break, okay? And this video is to talk a little bit more about how that pass factor is formed, okay? And that pass factor is an important part of the reachability information or route advertisements in BGP. So you want to also pay attention to this video.
Let's say more about the messages we exchanged in these BGP sessions. So these messages are essentially pass vectors. Inside the pass vector, we have lots of these pass entries, okay, or route entries. Each pass in the pass vector of BGP is this: the destination address. Now, because in BGP we are sending packets to a destination network, therefore, to address to a destination network, we use the prefix of the destination network. And then attributes. Now, in pass vector, the most important information there is the path. Therefore, you see, okay, in the set of attribute here, we need to definitely have the AS pass. So AS pass is the most important component in the set of attributes. There we see the list of ASs, okay, it takes from the source to reach the destination. The discovery of the list of ASs, the discovery of the AS pass, however, okay, came the other way, from the destination network. Okay, so the destination network is going to advertise its prefix, okay, and so that's going to be in an advertisement message. Okay, so the whole AS of the network X, okay, let's say AS2, okay, receiving such an advertisement at the gateway router, okay, that gateway router is going to prepend itself, okay, prepend the AS number, okay, AS number 3, okay, before X, and send this out as the prefix advertisement to the neighboring AS. The neighboring AS, let's say AS2 there, receiving such, okay, an advertisement, it's going to prepend itself before it sends out further to AS2's neighboring AS. Okay. So now AS2's neighboring AS receiving such an advertisement will then discover, right, a path to go from AS2, AS3 to destination X. Okay, so list of ASs through, okay, these paths, the prefix advertisements as traversed. Okay. So that is the AS path, one and the most important, okay, part in the attribute set. Second important is this, the next hop. Now, this is not quite, okay, the next hop AS, the next AS number, okay, in the AS path. No, it is actually the gateway router, okay, within the source AS that is directly connected to the next hop AS. So it's carrying the IP address, okay, of the gateway router, leading to the next hop AS. So the two together necessary forming the attribute set. Now, BGP routing, okay, has grown more and more being policy based, okay, meaning the gateway router, they're receiving these prefix advertisements. Okay, it's not like for every advertisements they will actually prepend its own AS and then pass it down further to other neighboring ASs. There'll be some sort of import policy. Okay, so the gateway there receiving the advertisements will have to say, okay, will have to decide. Some of the advertisements they will decline, and some others they accept. Only the ones they accept will be propagated further to all the routers within the AS. Okay. Now the gateway routers, okay, in the AS receiving these accepted, okay, advertisements will then decide whether to prepend themselves and then pass the expanded advertisements, okay, to the other neighboring ASs. Okay. But you see, there are also policy, okay, the AS might apply before these other gateway routers, okay, advertise the expanded, okay, AS path to the neighboring ASs. Okay, so some of them actually might have complex policy that is very fine-grained. For example, if one gateway router, okay, connects to two other neighboring ASs, this gateway router might say, I send this particular extended advertisements only to one of the ASs. Yeah. Policy to import and policy also to export.
Alright, so you see that BGP is essentially a policy-based routing because of all these constraints about what AS paths we import. And after prepending, what AS paths we export. Okay, so in these two processes, a lot of times we missed out the shortest AS paths. Okay, so you can imagine BGP routing on the internet. It's far less from being optimal, and it's more a business relationship. Much like when we were debating whether we would use distance vector or link state routing, the two of them. Previously, if you look at the performance perspective of these two routing algorithms, I think many of you choose distance vector. Okay? Even though you're told there are some disadvantages of using distance vector. Some stick to distance vector until you need to manage an autonomous system. Then all of you switch to link state. Yeah, because internet, it's privatized. Okay, it's not a system that is totally ideal. Okay, because it needs to work with people. It needs to be used by people. So in the end, you see that this BGP routing is a more human-centric routing algorithm. All right. So much of the later part of the lecture today is going to be about this policy. In fact, quiz 47 to 50 are all about routing policies. Okay, let's take a break, 10 minutes, and we'll come back to continue BGP routing. It's now 11:13. Let's resume the lecture 11:23. Break time. it's now 11:23, so that's resume the lecture. Okay, there's one more video to show that are just to show two more examples. Okay, so that get you into the mode of doing BGP. And again, it's essentially distance vector routing, but we not just advertise distance, but the path. And you hear from just the last video, not only the AS path, but the next hop and many other informations might also be in the advertisement messages. Okay, and the decision is not strictly the shortest AS path. Okay, policy based. Two more examples. Okay, make sure that you're familiar.
Let's go over a couple more examples so it's more clear where the import policy and the export policies are applied. So this is the same example we saw earlier. Destination network is here, X, okay? And so AS3 there is gonna send the past advertisement, okay? That looks like this, AS3, comma, X, okay? And this is gonna reach 2C of AS2. So AS2's router 2C receives past advertisements like this. And this is through the exterior BGP connection. And the advertisement came from AS3 and from router 3A. So 3A of AS3. Now, yeah, if you recall in the very early slide, right, the border router here will then propagate the AS path throughout all routers in the network. But no, there's import policy. So yeah, the exact process is more like this. 2C there will actually check AS2's import policy. If the policy says 2C, it's okay to accept the path, then 2C propagates the path to all routers internal of AS2. Okay. So sending of these AS paths internally is through the interior BGP connections. All right. So the import policy actually happens before the propagation of the path, okay, to all the routers internally. And then, 2A here, receiving such a path, can then prepend itself and pass it further to the neighboring ASs. But wait, yeah, the export policy is applied here before passing on of the advertisements. Yeah, let's check. If 2A here is allowed to advertise the discovered path to AS1 here, okay, then we form the new advertisement AS2, AS3, and X, and then send it to 1C that belongs to AS1. Okay, so once again, before the prepended, the extended AS path can be advertised further to the rest of the internet, we check the export policy. Right? Second example is a bit more realistic. So 3A here, the gateway router of AS3 might have multiple eBGP connections to outside. Okay, so in that case, a gateway router might learn multiple paths to a destination in AS3. So let's see. One of the paths is this, right? AS3's 3A sends AS3X, okay, as an advertisement to 2C. 2C checks the import policy and therefore pass it on to all the routers internally. 2A picks it up, checks the export policy, and let's say that it's just allowing advertisements of the path further. So prepend AS2 to the path and then send it further. At this point, 1C learns the path AS2, AS3 to destination X. And the way to go is for 1C to send to 2A. The other direction is this. 3A can be simply sending what? AS3X, okay, this past advertisements directly to 1C. And 1C will just simply learn, right? There's another way to reach destination X, which is just simply sending it to AS3 through 3A. Okay, so these are the gateway border routers that 1C send the packets to, okay, for the two different paths, 2A and 3A. At this point, 1C sees two advertisements coming in. Yeah, before 1C propagates any of the paths further, okay, it needs to check the import policy. Okay, so AS1's gateway router 1C there, okay, we need to choose. It could choose one of the two, or it could just take both of them. Okay, let's say that 1C chooses AS3, X. Yeah, sure, the shortest AS path. And advertise it to all routers internally of AS1. Okay. This is the second example.
So that second example is a lot more common on the internet, where you have ASs connected to multiple ASs. So very often to the same destination, you got multiple choices. Okay, so these import-export policies will be working together with the choices of the AS path as well. Okay, now next, BGP in detail. So what we have talked about is how BGP works, that is distance vector based and extended to path vector. Okay, and there's this policy thing that's interfering with the choice of path, which is often not the shortest. This is this. If you recall the overview videos about internet routing, we have inter-AS routing and intra-AS routing, and there's also interplay of the two routing. Okay, such that we can ensure data coming from an internal router inside an AS can still go outside of the AS. Okay. And that role, doing interplay between inter-AS routing, is the responsibility of the inter-AS routing, which is BGP. So a part of BGP routing is to define how BGP interplay with OSPF. And this is exactly what the next video is about. It's very short, 2.5 minutes.
Let me borrow example 2 here and continue to talk about this. How a router sets up a forwarding table entry, okay, for a destination outside of the AS. Okay. Yeah, scenario the same, destination being X. 3A, the gateway router of AS3 has 2 eBGP connection, therefore 1C here potentially can receive 2 AS paths. And 1C, according to example 2, chooses the shorter AS path. So let me run the animation. So 1C discovers 2 paths and picks the shorter path. Okay. And this shorter path is further propagated internally to all routers. So 1A, 1B, and 1D will learn about the shortest path to destination X from 1C. Okay. And what 1A, 1B, and 1D will do is, well, if I receive ever any packets with destination X, then I will forward the packet towards 1C, the border router, okay, they receive, okay, the AS path from. Okay. Now, to make it easier to explain what's coming up next, let me just label, okay, for 1A, if the packet is supposed to go out on this interface, then we call that interface 1. And yeah, for packets to go out on this other interface, let's call it 2. Okay, similarly for 1D, this is interface 1, this is interface 2. Now, 1D here, okay, has discovered there is a path to destination X that is going through 1C. Okay, that is what 1D knows so far. To add an entry into the forwarding table for X, 1D needs to know exactly which interface, is it 1 or 2, that leads to 1C. How would 1D know that? Yeah, call the intra-AS routing there. Okay, let's say it's OSPF. Okay, so OSPF is going to tell us if the destination is 1C, what is the link, okay, along the shortest path to 1C. Okay, so that happens to be 1, so we will fill this entry here. Okay, interface column being 1. Similarly, let's try to derive again for 1A. Okay, so 1A knows, yeah, for destination X, I should be forwarding packet towards router 1C. So let's call intra-AS routing and find out from OSPF, yeah, what is the shortest path to 1C and which link, is it 1 or 2 on the shortest path? And we'll get 2 here, and 2 here would forward packets to 1D. And 1D here we see earlier will be forwarding packets over this direction and reaching 1C. Therefore, yeah, going backwards and reaching destination X.
All right, so interplay of BGP and OSPF. The next video is going to be in 2 parts. Okay, the first is actually to talk about exactly how BGP routers select routes. So if you recall example 2, right, there are multiple paths you can choose from. Okay. After the import policy, the routers inside will still see, might still see, okay, multiple paths, but exactly which path okay, a router chooses. Okay, so there's actually a certain preferences, okay, and in hierarchies. So there will be multiple attributes the route selection is based on. Okay, that is the first part of the video, and the second part, okay, is to show you exactly how the internal routers of a domain chooses which gateway router to send the data to in case there are multiple AS passes available. You'll find it really funny, and that routing is called hot potato routing. Okay, so this video you see in two parts, a little bit long, about 6 minutes.
Route selection. Now, this mechanism is necessary for slightly more complicated scenarios. Let's go back to example 2 again. Right? We have this router 1C being the gateway router of AS1. So you see towards the end of the scenario, AS1 discovers 2 AS paths, one from AS3 to go to destination X, the other from AS2, and then via AS3 to go to destination X. So in the previous slide, we say the policy of AS1 is such that we only select this to import. And so 1C propagates this AS path to all internal routers. Internal routers will then send packets, destination being X, through 1C and therefore being forwarded to AS3. Very simple. But what if we relax the import policy a little bit further so that 1C here cannot discard this other AS path? As a result, 1C will need to propagate both paths internally. So each of these routers internally will see more than one route to the destination X. Ouch. Yeah, so that's when we apply the route selection. So internal router there will need to apply route selection here to decide which of these two it will send packets to. The process is like this. Step number 1, check the local preference of these routes. So if you recall earlier, a route is what? Composed of the destination network's prefix and a set of these attributes. So we know that AS path is one attribute. Next hop is one attribute. There's one more attribute called the local preference. So this one actually weighs the highest. So BGP actually checks the local preference first and take the path with the highest local preference. So local preference there is usually to indicate, between the two neighboring ASs, AS3 versus AS2, does AS1 prefer forwarding packets to AS3 or AS2? So if AS3 is preferred, AS3's path, so this guy here is going to carry a higher local preference. Now, if there's no local preference specified, then we go to step 2. So the internal router, let's say 1D here, will then check which of these multiple paths to destination X give us the shortest AS path. So in the scenario, 1D is going to pick this one. Now, if both AS paths have the same path lengths, then we go to step 3. We pick the closest next hop router. 1D here sees 2 paths. The next hop router for this path is going to be 1C. The next hop router for this path here is going to be 1C as well, because 1C is the border router receiving these advertisements. But if you consider a slightly different scenario, so again, we have AS3, AS2, and AS1. So the router now in the limma is now 2D. 2D here actually sees 2 AS paths. One AS path is actually coming from 2C. 2C is the gateway router connecting to AS3, which it receives a path to X, AS3, X. 2A is the gateway router connecting to AS1, where AS1 is passing another AS path to AS2. That is AS1, AS3, and X. So 2A pass this path to 2D. 2C also pass on this path to 2D. So 2D in the end learns, there's one AS path through next hop to A, this guy. There's another AS path through 2C, this one. 2D here Okay, assuming that abandon the shortest AS path phase, go straight to the closest next hop router phase. Then we'll do this. For this path, next hop router is 2A. For this path, next hop router is 2C. 2D here will consult, okay, the intra-AS routing again to find out is 2A closer or 2C being closer. So if you see the scenario, 2A distance to 2D is only the link cost between 2A to D, which is 201. Distance between 2D to C, however, is 263. So 2D here is going to choose 2A to forward the packets to. So it's going to choose AS1, AS3, and X, this other AS pass, which is actually longer, okay, than this other one to pass the data. This is also very well known as the hot potato routing. Allow me to explain. Yeah, so 2D is this guy holding a hot potato. So yeah, the packets are almost like these hot potatoes, and 2D can't wait to get rid of these packets. So 2D wants to be able to pass the hot potatoes, the packets, as soon as possible. Therefore, picking, okay, this poor guy here, 2A, to throw all the hot potatoes over. Okay, distance is shorter.
All right. Now you see, it actually makes sense to do hot potato routing because shortest AS path doesn't mean that it's the shortest path, isn't it? Because the amount of effort to transmit the packet in an AS could be so large that it might be longer than passing the data to two small ASs. So shortest AS path doesn't make much sense. Okay, the cost might be higher. Therefore, greedy solution, hot potato routing. Okay, whichever gateway is closer to me, I forward, okay, the data to the shortest distance gateway router. Okay, and this is under the assumption that both of these gateway routers knows a path to the destination. All right. Last about BGP, before we talk about the policy, is just a short video, 2 minutes, to show you the BGP messages. Okay, there are 4 kinds.
This is the last slide of the BGP protocol. Okay, so in BGP, the protocol, it actually defines 4 types of messages. Okay, so not just the message we mentioned earlier containing the pass factor being passed in the BGP sessions. Okay. There are other types of messages that BGP sends. So some of them are actually to send the pass advertisements, to send the pass factors, but some of them are to establish the TCP connections, okay, for the session, or to tear down the TCP connection, or to keep the TCP sessions alive. Okay, let's go through these BGP messages. The first type is called the open message. Yeah, the first purpose of it is to establish the TCP connection. Okay, so the sending peer there will be sending an open message to the receiving peer. Okay. Receiving peer will be sending back an ACK for that message. As a result, the 2 peers establish a BGP session. So the ACK of the open message there is going to be in the keep alive message format. Okay, I know it's a bit tricky. Now, the open message is also used to do the authentication. Okay, so the 2 peers can authenticate each other to make sure that the pass advertisements, okay, are indeed the true pass, okay, to be discovered. Now, update message. So this is the message being used to send the past advertisements, the past factors. So this message is also allowing the routers to withdraw outdated pass factors. Keep alive message we saw earlier, it's to ACK the open message to establish a TCP connection. Keep alive message is also being sent, okay, periodically to refresh the TCP connection, just in case there's no update messages being generated. So update messages is, yeah, the past advertisements. Last is the notification message. Okay, so this reports in case there's any error in the previous message. Okay, and it's also used to close the connections for the peers.
All right, so just keep in mind, in BGP, all these eBGP, iBGP sessions, there are TCP connections. Okay, hey, some of you might be thinking, wait a minute, BGP is layer 3 protocol, but TCP is a layer 4 protocol. A layer 3 protocol is actually depending on layer 4 protocol. What's going on here? Well, guys, that's the way it is now. All right, so let's move on to the final topic. Okay, and this video is long, almost 7 minutes, and it's talk about BGP being a very policy-based routing protocol.
One very important issue about BGP to discuss here is, BGP routing is very policy-based these days. If you recall, there's import policy, there's export policy, there's also local preference for route selection. There are lots of things the network admins can tweak, to decide where packet goes. The reason for those policy-based settings is this. Let me use an example to explain. Consider this network. We have 3 ISPs in the middle, ABC, they are the provider networks. W, X, Y are the customer networks. More specifically, W is the customer of ISP A. So W pays A some amount of money every month, and A will in turn help W passing packets, going out to the rest of the internet or coming in from the internet. Similarly, if the traffic is supposed to go out the other direction, right? So W pays A, and therefore A is responsible to serve W. Similarly, for this customer-provider pair, Y being a customer, C being a provider. X being a customer, B being a provider. Now, X is a little bit more complicated. It's multi-homed, customer network. So X here pays B and C. As a result, B and C should both be forwarding packets for X. In scenario 1, let's assume that there's a user in customer network Y here wanting to send something to the user in W. And so in order for W to draw in traffic from the internet, its provider A here will need to announce its existence. So AW here, an AS pass needs to be sent to the neighboring ASs, which happen to be ISP B and ISP C. So A advertises pass AW to B and to C. As a result, B is going to see this pass and prepend itself and see if this AS pass needs to be further advertised to yet another neighboring AS, such as provider C. Now, B's network admin actually knows better and choose not to do that. And the reason for that is because of this. If BAW is advertised to C, C is going to discover, this is actually one way for this user in Y to send traffic to user in W. And therefore, the traffic is going to go this way to W. And you know what? B here, B does have a customer X. X is paying B. But is W paying B? Is A paying B? Is C paying B? Well, based on the setup of the problem, WAC not paying B, and yet B is using the network resource here to transit the traffic for B and C. So B gets no revenue to do this route, BCAW, because CAW, based on the scenario setup, not paying B. So chooses not to advertise BAW to C is so that C does not discover this pass, and therefore, not using this pass to send traffic. Instead, C here receiving AW is going to prepend itself CAW, and Y is going to use CAW as a way to send traffic to the user in W. So you see in this scenario, very obvious. For a customer network, ISP will be happy to route traffic to and from the customer. But the ISP not getting paid by others would hate to transit traffic between these other ISPs. So bottom line, not getting paid for the work. Scenario 2 is very similar to scenario 1. The network is completely the same, and we just continue scenario 1 from here. When B has discovered BAW is a pass to go from B to W. Now back in scenario 1, a min of B chooses to not forward BAW to C. so that we don't draw traffic this way. Nice. But B will actually have to send BAW to X. So X can discover XBAW is a pass. So just in case there's any user in X wanting to send data to user in W. Nice. So makes sense. But hey, X is dual home, so there's yet another connection to a neighboring ASC. So should the network admin of X here send XBAW to C? Well, let's assume that we send XBAW to C. In this case, C is going to discover CXBAW is a pass to send data to W. Similarly, Y is going to discover YCXBAW is a pass to send traffic. YCXBAW is a pass to send traffic from a user in Y to a user in W. And that's going to travel like this. How do you like this? Well, from the X's network admin's point of view, hey, this traffic is actually not for me at all, right? It's actually between Y and W. Y pays C, W pays A, and no one is paying me, and yet I'm paying B and C. Okay, so it's a big no-no for X here to send XBAW to C. All right, so X will not want traffic coming from C and simply transiting to B. So X should not be advertising anything to C, okay, coming from B. So again, money is the issue, all right? So X is not getting any money from C or from B. Therefore, X is not happy transiting traffic for these other ISPs or even from other customer networks not paying.
All right. How do you like BGP's policy-based routing? It sounds like it's a human routing. The solution is no longer computerized. Okay, we have no role in setting these routes. Okay, at the BGP level. If you had this intuition, you're perfectly right. Being a privatized, being a business, the internet is, the routing is very business oriented. Okay, bottom line, $sign. And to illustrate that, or to allow you to exercise how to set the routes for BGP, okay, we are not going to be talking about link state routing or distance vector routing where we are looking for shortest path. I'm actually asking you to exercise, okay, your business intuition. Okay, from 47 to quiz 50. Okay, you will see whether you would do well in the business school. All right, so the first one, hey, this is the easiest one. Okay, you see that we have a network here. It's actually easier than the example on the video, isn't it? So similarly, we have A, B, C being the provider network, X, Y, W being the customer network. And for quiz 47 all the way to 50, Y here often sends data to X. So Y here sends data to X. All right. So we know X being the customer, X pays B. So X here, the customer network, and a customer of B provider. X pay B money. B being the provider, receiving money from X, will need to forward traffic both direction, from X as well as going to X. Okay? So B charges X not only to forward traffic out, but also forward traffic in. Okay. Q1. Should B advertise the AS pass BX to A. So the goal is Y needs to send traffic to X. So X will start advertising its existence, right? So X will say, hey, I'm X, I exist. And B will receive X and prepend itself. So there's a BX pass being formed here. Should B advertise BX to A? That is Q1. And what's more important that Polly is looking at is, why do you think, okay, it needs to or it doesn't need to? Okay. And hey, by the way, from quiz 47 to 50, there's no one answer. All right, it's very open end. You argue, okay, based on your business or engineer's intuition. All right. So tell me why you think it should or it should not. Q2. Now, in case B does advertise BX to A, should A advertise ABX to C, and why? Okay, and this is quiz 47. Let's go to the score, channel W15, quiz 47. Oh, okay, I see. Mark already posted the solution, all right. You know what? You guys are given 2 minutes, okay, to think about it and type up your solution. And let's start. Okay, now we can see already. So obviously for Q1, B will need to advertise BX because B gets money from X, right? B needs to definitely let people know the existence of X, okay? Now Q2 is a little bit tricky, isn't it? So you see Mark here says yes and no. If A wants to be a good member of the internet, yeah, so you help advertise that, okay? If it cares only about revenue, no. So Mark, you will do well in engineering as well as business. And Doris, on the other hand, hey, you, Doris, a perfect engineer thinking. Hey, otherwise, Y doesn't get to send data to X. Okay, so Doris, you've chosen to study electrical engineering. Well, Ethan, you're misplaced. You would do great in business school, Ethan. Yeah, okay, so yours is Ethan, not Ethan. Okay, so yeah, it's a little bit different. Ethan. 健身 not car. Okay. Yeah, okay, so business intuition says no. However, if A doesn't send ABX to C, then hey, X gets no data. Okay, so it's a no with a little bit of consideration. Okay. Okay, Jin Yang wants a better network. Oh, okay. Jin Yang, I think you're probably a little bit socialistic. Yeah. Is internet a public infrastructure or private infrastructure? Is it a shared resource or is it a fully privatized resource? You know what, Jin Yang? That is a subject still an ongoing debate. Some people said that internet cannot be strictly private. Okay, so these business owners, the ISPs, they cannot be thinking purely based on profit. Okay, they need to also think what's fair. Okay, and if they don't want to be fair, chances also that others don't want to be fair, and you might end up sending data in a disconnected internet. Ouch, ouch, ouch. That hurts, right? Just observe the international relationship recently. Okay. Operation of the internet. It's not strictly engineering, you see. It's also not strictly business, you see. But then how? What is it? Okay, so you guys like to ask questions like this, right? It's complicated. It is. Therefore, there's no one solution. Okay, it's actually more that collective wisdom of the human beings living in the world, on this planet. Okay, so my suggestion is be kind. Then we stay connected, then disconnected. All right, good. I see that you guys all have a lot to say. This is great. Okay, that is the point of college. Okay, now let's move on to the second quiz, 48. Okay, I have an idea that you like these 4 quizzes. Okay, yeah, so what do we see here? The network is back to be a little bit complicated. So you see that there's a link between B and C. So it's a cyclic network now. All right. And we know for sure already that B advertises BX. Okay, being a provider of X, B must do this. All right. And so the final goal is still that Y needs to send data all the way to X. So Q1 here, ask. A and C charges B equal an amount of money per bit. Where's A? A here. C here. A and C are 2 other providers connecting to B. Okay, so there are the potential receivers of advertisements BX. Okay, if A and C charges B equally for every bit, okay, A and C needs to forward. All right. Suppose now you are hired by B. Okay, you're now working for B, and you want to make sure that B gets the maximum profit. Should B advertise BX to only A, only C, both, or at least one of them? Okay, I think the key point that I was looking for, the key answer I was looking for is Y. Q2, oh, wait. C and A now begin to charge B differently, and C asks B for more. A charges less. So B sees here, oh, A is cheaper, C is more expensive. Suppose you are hired by B. Would you advertise BX to A only, to C only, or both, or at least one of them. Okay? Again, key point is why. So let's go to channel W15, quiz 48. Okay, for this one, you have also just 2 minutes. Okay, go. Yeah, you see here, Jin Yang, very unique. So for Q1, he says, yes, I guess send to both A and C, right? So the customer bought access of internet. So what I mean, sends advertisements to all around the internet. And if A and C are both connected, then definitely, okay, send to both. Okay. And besides, the price is the same anyway, right? So whether C or A is forwarding the traffic, either way is fine. Now, for Q2, okay, this is very, very business thinking. How about changing the charge to X? Oops. Okay. How about changing the charge to X such that if the traffic goes through A, it's lower. If the traffic goes through C, is higher. Much like how A or C is charging B. All right. And Mark here says at least one of them feeding obligation. Okay. Yeah, so of course, C needs to send at least one of them. Okay. Which includes maybe both. Okay. And given that AC charged the equal amount of money, then which one doesn't matter. And Mark here is thinking for Q2, advertise only to A because you save money. And this is definitely thinking on behalf of provider B. Okay, and you're gonna be a great employee. On the other hand, Jin Yang, a little bit socialistic, but I think the company will still be happy. Okay. Let's see, Walker. Both, yeah. You know what? Just send to both of them. Maybe A and C have certain import policy. They might not take the advertisement anyway. Yeah. So both here, best effort. A, since A charges me less, treats me better. Okay, good. So this is very business-oriented solution. All right, so hey, whatever you decide to pursue, give the reason. Okay, so How about that? Move on to the next quiz. 49. Okay. Yeah, Polly is going a little bit fast today. But you know what? Yeah, these quizzes are all very interesting. Let's see. 49. Net weight is the same. Oops, sorry. The net weight is the same. Okay. We know already, okay, B advertises BX to A and C, both of them. And A advertises ABX to C. Okay, so this is presumption. It has already happened. So C here, therefore, learns two paths to reach X for Y. One is CBX, right? B advertises BX to both of them, therefore C knows CBX is a way to X. A also advertises ABX to C, so C knows two ways, CBX, CABX, CBX, CABX. Okay, now C charges A more and charges B less. So look at the money flow. C draws more money from A per unit data. C draws less money from B. Okay, suppose you are now hired by C. Okay, guys, no longer working for B, now working for C. Question, would you advertise CABX or CBX or both to Y and Y? Okay, let's go to channel W15, quiz 49. Again, oh, wait a minute, guys, it's time already, all right? So, hey, guys, quiz 59 is gonna be a take-home, okay? And so is quiz 50. Okay, allow me to borrow just a little bit time to go over quiz 50 so you understand what quiz 50 is asking. Okay, quiz 50. Okay, the point is to let you know that it's a money game, unfortunately. Based on the setting from 48 and 49. Okay, 48 and 49. Consider money. CABX will be the path to forward traffic from Y to X. CABX, right? From 49, this is the cheaper path. Actually, no. This is the path that C earns more. Look at the money draw. B, forward to A because A charges B less. So C here, obviously, would try to do this. Okay. But then, now, in case you are hired by A here, A is charged by C more, and B pays A less. Would you raise or lower the price charging B? And as A, would you raise or lower the price paying C? Q3. Any other solution to prevent A from being ripped off by B and C? That's quiz 50. So again, the key point is telling why. All right. So that is all about internet routing. So in the end, we learned so much about BGP, but it's really human computing, not computer computing. So these algorithms we use in distance vector doesn't really apply in the end. All right. So with that said, guys, I say goodbye for the semester, but I will see you, okay, next Wednesday for the exam. So that's all. There's office hour Wednesday noon. So in case you have questions, feel free to pop in and ask. And that's all. Bye. See you next Wednesday. And music. Bye. with the final. Bye. We don't. Okay, bye. Okay, thank you. You guys are all very kind as well. Glad that you guys listened. Okay. All right. Okay. Okay, go get lunch. And enjoy the summer, okay? Do play, do have fun. center stream.